Welcome students to the present lecture on the topic Ionic Equilibrium Part 1st. In this lecture, we will discuss the following topics: physical and chemical equilibrium, ionic equilibrium, electrolytes and their types, ionization constant and factors affecting it, and self-ionization of water. Equilibrium represents state of a process in which the properties like temperature, pressure, concentration of a system do not show any change with the passage of time. The equilibrium achieved in physical processes such as dissolution of salt, evaporation of water, etc. is called physical equilibrium, whereas the equilibrium achieved in chemical processes like decomposition of calcium carbonate, formation of ammonia, etc. is called chemical equilibrium. Ionic equilibrium. This type of equilibrium is observed in substances that undergo ionization easily or in polar substances in which ionization can be induced. Ionic and polar substances are more easily soluble in polar solvents because of the ease of ionization taking place in the solvent medium. With the dissolution of ionic and polar substances in the solvent, these solutions become rich in mobile charge carriers, that's ions, and thus can conduct electricity. Substances which are capable of conducting electricity are called electrolytes, while those substances which are non-conducting are called non-electrolytes. An electrolyte is a substance that dissociates into ions in solution and acquires the capacity to conduct electricity. Sodium, potassium, chloride, calcium, and phosphate are examples of electrolytes. Electrolyte replacement is needed when a patient has prolonged vomiting or diarrhea as a response to strenuous athletic activity. Electrolyte solutions are normally formed when a salt is placed in a solvent such as water and the individual components dissociate due to the thermodynamic interactions between the solvent and solute molecules in a process called solvation. For example, when sodium chloride, which is commonly called table salt and represented by the symbol NaCl, is placed in water, the salt, which normally is a solid at room temperature, dissolves into its component ions. According to the dissociation reaction, NaCl solid gives Na positive ion aqueous plus chloride negative ion aqueous. It is also possible for substances to react with water producing ions. For example, carbon dioxide gas dissolves in water to produce a solution that contains hydronium ion, carbonate and hydrogen carbonate ions. As per the chemical equation, CO2 plus H2O gives us H3O positive, which is the hydronium ion, plus CO32 negative, which is the carbonate ion, plus HCO3 negative, which is the bicarbonate ion. The electrolytes are of two types: strong electrolytes and weak electrolytes. A strong electrolyte is a solute that completely or almost completely ionizes or dissociates in the solution. These ions are good conductors of electric current in the solution. A concentrated solution of this strong electrolyte has a lower vapor pressure than that of pure water at the same temperature. Strong acids, strong bases, and soluble ionic salts that are not weak acids or weak bases are strong electrolytes. For strong electrolytes, a single reaction arrow shows that the reaction occurs completely in one direction, in contrast to the dissociation of the weak electrolytes, which both ionize and rebond in significant quantities. As per the chemical equation, strong electrolyte in its aqueous form gives cations which are positively charged in their aqueous form and anions which are negatively charged in their aqueous form. A strong electrolyte is nearly completely dissolved as ions. More than 99% of it is dissolved in the ionic form and not as an associated unionized compound, which is less than 1%. Weak electrolytes. Weak electrolytes are substances that only partially ionize in aqueous solutions. Weak electrolytes are those electrolytes which dissociate only partially in water solutions, giving ions which are in equilibrium with undissociated molecules. For example, acetic acid partially dissociates into acetate ions and hydrogen ions, so that an acetic acid solution contains both molecules and ions. A weak electrolyte forms only a few ions, less than 1% in solution, with most of the compounds staying in a non-ionic form. That's greater than 99% stays in the non-ionic form. Examples of strong and weak electrolytes are strong electrolytes. Strong electrolytes may be strong acids, strong bases, or salts. Amongst the strong acids, we have various examples. For example, hydrochloric acid, symbolically represented as HCl, hydrobromic acid represented as HBr, hydroiodic acid represented as Hi, nitric acid represented as HNO3, perchloric acid represented as HClO4, and sulfuric acid represented as H2SO4. Amongst the strong electrolytes, we also have strong bases such as sodium hydroxide represented as NaOH, potassium hydroxide represented as KOH, lithium hydroxide represented as LiOH, barium hydroxide represented as BaOH whole twice, and calcium hydroxide represented as CaOH whole twice. We also have strong electrolytes in the form of salts such as sodium chloride represented by the formula NaCl, potassium bromide represented by the formula KBr, magnesium chloride represented by the formula MgCl2, and many more. Then weak electrolytes. Weak electrolytes are also of different types. We may have weak acids as weak electrolytes, or we may have weak bases as weak electrolytes. Amongst the weak acids, we have hydrofluoric acid represented by the formula HF. We have acetic acid represented by the formula C2H4O2. We have carbonic acid represented by the formula H2CO3. We have phosphoric acid represented by the formula H3PO4, and many more. We have weak bases also as weak electrolytes. For example, ammonia represented by the formula NH3, pyridine represented by the formula C5H5N, and several more. Ionization of weak electrolytes and degree of ionization. Weak electrolytes are ionized only partially. The ions produced as a result of dissociation of weak electrolytes are present in dynamic equilibrium with the undissociated molecules as given by the equation AB aqueous gives A positive aqueous plus B negative aqueous, where the reactants and products are in equilibrium. The extent of ionization of weak electrolytes is often expressed in terms of the degree of dissociation alpha, which gives a quantitative estimation of the extent of ionization. Oswald dilution law and degree of dissociation alpha. The fraction of total number of molecules of electrolyte dissolved that ionizes at equilibrium is called degree of ionization or degree of dissociation. It is also defined as the ratio between the number of ionized molecules and the number of molecules dissolved in water. Numerically, alpha is equal to the number of molecules dissociated divided by total number of moles taken. As per Ostwald dilution law, alpha is equal to square root of K/C, where K is the equilibrium constant involved in the reaction as already shown and C the concentration of the solution. So, the degree of ionization is inversely proportional to concentration. Thus, as the concentration decreases, the degree of ionization increases. It can also be followed from the above relationship that as C approaches 0 or dilution approaches infinity, the degree of dissociation approaches unity, that is its maximum value. In other words, in a very dilute solution, the whole of electrolyte is present in dissociated form as ions. Degree of ionization or dissociation alpha. The degree of dissociation alpha is a way of representing the strength of a weak acid or a weak base. It can be represented as a decimal number or as a percentage. One can classify strong acids as having ionization degrees above 50%, weak acids with alpha below 50%, and the remaining as moderate acids at a specified molar concentration. There are various factors which affect the degree of dissociation or ionization. At normal dilution, value of alpha is nearly unity for strong electrolytes, while it is very less than unity for weak electrolytes. Higher the dielectric constant of a solvent, more is its ionizing power. Water is powerful ionizing solvent as its dielectric constant is highest. The degree of ionization is inversely related to the concentration of the solution as well as to the weight of the solution. Numerically, we can show that alpha is inversely related to the concentration of a solution, or it's also inversely related to the weight of a solution. It also amounts to saying that the degree of ionization is directly related to the dilution of the solution as well as to the amount of solvent. Degree of ionization of an electrolyte in solution increases with the rise in temperature. Presence of common ion. The degree of ionization of an electrolyte decreases in the presence of a strong electrolyte having a common ion. Self-ionization of water and the concept of ionic product of water. Water is a weak electrolyte. Even in pure state, water is weakly ionized to give hydronium ion, which is represented symbolically as H3O positive aqueous, and hydroxide ion, which is represented symbolically as OH negative ion aqueous. As shown in the equation, H2O liquid plus H2O liquid, that means two molecules of water, they undergo autoprotolysis to generate H3O positive aqueous, that is hydronium ion, and OH negative aqueous, that is hydroxide or hydroxyl ion. Applying law of chemical equilibrium, we have a numerical equation K is equal to product of concentrations of hydronium ion H3O positive and hydroxyl ion OH negative divided by square of the concentration of water H2O. Since concentration of water H2O may be taken as constant because it practically changes very negligibly and thus may be combined with K to have another constant which is called Kw. numerically we may have K into square of concentration of water is equal to the product of concentrations of H3O positive hydronium ion and OH negative, that's hydroxyl ion. Or we can have Kw is equal to the product of concentrations of hydronium ion and hydroxyl ion. The constant Kw is called ionic product of water. Its value at 298 Kelvin is 1.008 into 10 to the power minus 14 mole square per liter square. In pure water, hydronium ion concentration and hydroxyl ion concentrations are equal. Therefore, ionic product of water Kw is equal to the product of concentrations of H3O positive and hydroxyl ion. Since the concentration of hydronium ions is equal to the concentration of hydroxyl ions, we can have Kw is equal to square of concentration of hydronium ion. Or we may have hydronium ion concentration is equal to square root of Kw, which means ionic product of water. At 298 Kelvin, the concentration of hydronium ions is equal to the square root of 1.008 into 10 to the power minus 14, which is equal to 1 into 10 to the power minus 7 moles per liter. And similarly, hydroxyl ion concentration happens to be equal to hydronium ion concentration is also equal to 1 into 10 to the power minus 7 moles per liter. Since with increase in temperature, dissociation of water increases, therefore, value of Kw increases as the temperature is increased. However, at all temperatures, the concentration of hydronium ion remains equal to hydroxyl ion in pure water. Concentration of hydronium ion and hydroxyl ions in aqueous solutions of acids and bases. Hydronium ion represented as H3O positive and hydroxide ions represented as OH negative ions are always present in the aqueous solution, whether it is acidic or basic. However, the relative concentrations of these ions vary in different solutions. In general, in neutral solutions, the concentration of hydronium ion is equal to the concentration of hydroxyl ion. In acidic solution, the concentration of hydronium ions is greater than the concentration of hydroxyl ions. In basic solutions, the concentration of hydronium ions is less than the concentration of hydroxyl ions. Strength of acids and bases or dissociation of acids and bases. Strength of an acid is measured in terms of its tendency to lose proton, whereas strength of a base is measured in terms of its tendency to accept proton. An acid is considered to be strong if it has great tendency to lose proton. The conjugate base of a strong acid is weak base. We may show the chemical equation: hydrochloric acid HCl aqueous reacts with water H2O liquid and it generates H3O positive aqueous plus chloride ions Cl negative aqueous. HCl happens to be a strong acid, donates a proton to water and generates chloride, which is a weak base. On the other hand, conjugate base of a weak acid is a strong base. We may show the equation: acetic acid CH3COOH aqueous plus water H2O. They react together and they generate H3O positive aqueous, which is hydronium ion, plus acetate ions CH3COO minus. The acetate ions generated from acetic acid is a strong base because acetic acid itself is a weak acid. The strength of acids or bases is experimentally measured by determining its ionization constant or dissociation constants. Strong acids dissociate almost completely in water, and therefore the molar concentration of hydronium ions in the solution are same as that of acid itself. But weak acids are not completely dissociated, and the relative strengths of weak acids can be compared in terms of their dissociation constants. For example, the dissociation constant of an acid HA may be represented as HA aqueous reacts with water H2O liquid. It generates H3O positive aqueous hydronium ion plus A negative ion, which is in its aqueous form. Applying law of chemical equilibrium, we have the equilibrium constant K for the above reaction is numerically equal to the product of concentrations of hydronium ion H3O positive and A negative ion oblique the product of concentrations of HA and that of water. Since concentration of water is very large and remains almost constant in solution, it can be combined with K to give another constant which is called Ka. Numerically, we have K into concentration of water is equal to the product of concentrations of hydronium ion and A negative ion oblique the concentration of HA. From this equation, we have Ka, which is another constant, a multiplication constant of K and concentration of water is equal to the concentration of H3O positive, that is hydronium ion, into the concentration of A negative ion divided by the concentration of the acid, that is HA. Here Ka is called dissociation constant of the acid. The value of dissociation constant gives an idea about the relative strength of the acid. Larger the value of Ka, higher is the concentration of H3O positive and stronger is the acid. If dissociation constants of two acids are known, their relative strengths can be predicted. For example, larger the value of Ka, that is the acid dissociation constant, higher is the concentration of H3O positive, that is hydronium ion, and stronger is the acid. If dissociation constants of two acids are known, their relative strengths can be predicted. For example, the acid dissociation constant of acetic acid is equal to 1.8 into 10 to the power minus 5 at 298 Kelvin, whereas the acid dissociation constant of hydrofluoric acid HF is equal to 6.4 into 10 to the power minus 4 at 298 Kelvin. Since the acid dissociation constant of hydrofluoric acid HF is greater than the acid dissociation constant of acetic acid, that is CH3COOH, therefore HF is a stronger acid than acetic acid CH3COOH. With this, we conclude our today's topic. Thanks for watching.